Okay, so today we are going to discuss something about generally about meshes for CFD. What type of meshes do we have available in for CFD simulations, and what are the general guidelines for creating a quality mesh? So you have already gone through some tutorials as well, and you have experienced that mesh is a prerequisite for any simulation, whether it's finite difference method or finite volume method. You have to first create the mesh or discretization of the domain. So a good quality mesh has a direct impact. A good quality mesh can enhance the accuracy of the solution and also the convergence rate of the your flow simulation. It is complicated process, and as we move towards more complex geometries, the mesh or discretization of this space becomes hard to action. You probably have experienced yourself that even for simple geometries, it takes a lot of time to first decompose, discretize the space, and then create a mesh. So it's probably one of the most time-consuming steps in all of the CFD simulations. And so that's why nowadays the thrust is towards semi-automatic or automatic generation methods, and probably fully automatic unstructured meshing will be the future. So there are various choices available. First main classification is between a structured mesh and an unstructured mesh. We'll see it later. Gone through yourself in the tutorials as well that we create structured meshes in the start, and then in the last tutorial about 3D we created an unstructured mesh. So that is the first choice, whether to create a scope for a structured mesh or unstructured mesh. This is influenced by many factors. First and foremost is the compatibility with the flow solver. So whether your flow solver can handle structured mesh or unstructured mesh, and whether your numerical scheme, most precisely the numerical scheme which you have written, whether that is for structured mesh or unstructured mesh. For example, if your code is based on finite difference method, then most probably you will be using a structured mesh, because unstructured mesh FTM is very complex and it's not commonly used for unstructured meshes. We commonly use finite volume method. So Fluent, for example, can handle both structured meshes and unstructured meshes. So it's based on finite volume method. Second choice is whether you will be adopting your mesh or not later on. Mesh adaptation means whether you'll be locally defining the mesh or moving some elements to more critical areas, etc., or de-refining some areas of the mesh based on the flow activity. For example, if you have high flow gradients or shock waves somewhere, then obviously to capture those shock waves more accurately, you want to refine the mesh only in that region. So that is called mesh adaptation. That is another important area of research nowadays. The word mesh and grid, they are both used interchangeably. So basically the same, they both have same meanings. How we can define a mesh? So more formal definition is a set of points for FTM and set of volumes for finite volume method, which replaces the continuous real space. by a finite number of isolated points in space or isolated or discrete volumes in space. So here I'm going to talk about two main types of meshes we can have. First one are the structured mesh or structured grids. Second one is unstructured meshes. So a structured grid has basically it's composed of families of intersecting lines, one for each space dimension. For example, for 2D, you will have lines for x-axis and lines intersecting, those lines will be intersected by the lines in the y-axis, so that each intersections, family of intersection will create a 2D 2D square or 2D rectangle, and 3D will create a cube or a hexagonal mesh. An informal definition you can have is that a structured mesh in a structured mesh, each node or vertex shares equal number of neighbors, share equal number of cells. So, for example, if you have a 2D mesh, then each node will have 4 cells attached to it. Okay? But in unstructured mesh, this number varies from node to node, where you can't necessarily have equal number of cells attached to a specific node. Okay? So that's the main difference between a structured and unstructured mesh. Okay, what are the advantages of creating a structured mesh? Generally, a structured mesh is attributed to more accuracy and less space storage, because when you write the routine, when you create the mesh, you have to store the information of nodes, its coordinates, and its neighbors. Okay, so this storage requirement is far less because there is a pattern, the structured mesh, and the algorithm which you will be writing. You can the information in the form of arrays which you will be storing is sort of more systematic. Okay? So therefore, you can have store the information about the structured mesh in a more systematic manner, which requires less space. So that is one of the advantages. Of course, when you're creating billions of cell size mesh, these considerations become important. Secondly, it has been found that it is structured meshes often result in more accurate solutions as compared to the similar unstructured meshes. So they are the two main advantages. And the restrictions can be that, as I said before, for finite difference method, or if your solver is only written to handle structured meshes, then of course you will be using structured mesh only. Disadvantage that structured meshes can only be applied to relatively simple geometries. As we have seen before, you can create, for example, the flow in a pipe or over aerofoil or something like that. So very simple geometries, or even for moderately complex geometries, you can create structural mesh, but it will take a lot of time because you have to first create a blocking topology, like you have to split the domain into a number of blocks and then create a structural mesh separately for each block. So it takes a lot of time, and sometimes this blocking is cumbersome, or sometimes it's not even possible to block it efficiently. So there comes the unstructured meshes. We'll talk about that later. Here's an example of a number of 3D structured meshes. For example, you have a landing gear mesh here. You have a lung passing mesh, a turbine blade mesh, and a close-up of this mesh. So all of these meshes have been created by multi-block structured meshing. So first you have to create a block for each of the entity of this geometry. Then you create the mesh on each of these blocks. Okay, so in this main category of structure meshes, and then you have a number of subcategories or sub-classifications. And the first one is the Cartesian mesh. So as the name suggests, it's like a Cartesian coordinate system mesh where you have this orthogonal x-axis and y-axis and z-axis type uh, z-axis type mesh. For example, the first mesh which you created for simulating pipe flow, it was a Cartesian mesh. So more formal definition is that in a Cartesian mesh, all the points are equidistant and the cells in 3D are perfect cubes and in 2D they are perfect spheres. So with delta x, delta y, and delta z being good. And they generally have the highest possible accuracy and they can be equally applied to finite difference method and finite volume method. Okay, but what is the limitation over here? That they can only be applied to those geometries which are aligned with the Cartesian axis, for example, 2D or 3D. Simple channel flow, which have a rectangular domain. There you can see you can apply it. But as the geometries becomes more curvilinear, they are curved shape or they become complex, then there it's difficult to apply Cartesian meshes because there you won't be able to split it in a perfect sphere shape or perfect cubic shapes. Okay, so here comes the next point. When curved solid surfaces are present, they cannot be part of the Cartesian mesh lines. So there we need to adapt. And there generally we have two options. Either we keep the Cartesian structure, and when we introduce and when we come close to the solid boundary, like wall or something like that, which is a curved shape, then we have to apply special treatment. Or we move away from second option is that we move away from this perfect Cartesian structure and create body fitted grids. So we'll see that later one by one. Okay, so first option can be a variable mesh size. The delta x is not equal to delta y, and the mesh is more refined in where, for example, you will have this separation here, or here you will have a complicated flow pattern. So there, mesh has been refined. So this is one of the adaptation which we can do to accommodate or capture flow physics more accurately. Okay. Second, so here we have a curved surface now in the form of an airfoil. So one of the options is to create a quad tree structure. What is a quad tree structure? Is again it's a Cartesian type mesh, okay, but away from this body, the mesh is coarse. Okay. And as we move closer to the body, which is, for example, here we want to capture flow physics more accurately, we gradually refine our mesh. So the structure, overall structure is Cartesian, but as we are moving closer to the body, the mesh is being refined. And here we have, to capture this surface, we have this staircase representation, which might not be very accurate, but if we keep on refining this staircase, we'll be uh, capturing the curvature of the surface more and more accurately. But this is not a very ideal uh, situation. But this can be one of the options. The other feature here is the presence of hanging nodes. Hanging node means that mesh is not matching with each of the cells. Okay? So here we have this node over here, which is not attached to any other node upward. Okay? So this is called hanging node. And normally your flow solvers are written to avoid these hanging nodes. Normally you have this one-to-one matching of the nodes. But in order to cater for hanging nodes, you have to have a provision in your mesh solver, in your flow solver, to cater for hanging nodes. And very specialized codes are available for very specific applications where people see an advantage in using quad tree or off tree approach. And there the flow solver is also adopted to account for hanging nodes. So in 2D, the mesh, this technique is called quad tree based meshing, and in 3D, this is called off tree based meshing. So within this off tree quad tree approach, there are further subcategories. One is very famous method, which is called immersed boundary method. So in this one, we don't respect this boundary. So this is solid surface. So ideally, you would have created a mesh around this. Okay? But in immersed boundary method, we also mesh crosses the boundary. And how to capture this effect of this surface then, or this region? In the flow solver, some specific numerical procedure is defined which handles the physical boundary conditions. So what does it mean? It means that the meshing is relatively simple, but then to account for the presence of boundary effect of this boundary, you make special treatment in the flow solver itself. Second one is staircase shape. We have already discussed this before, that you go for this staircase representation as the curvature is changing. And the third option is within the quad-tree approach is to use cut cells. Cut cells means that away from this solid surface, you have perfect squares or Cartesian meshes. But to account for this surface, you cut your cells to adapt to the curvature of this. So for example, here we had a perfect sphere, a perfect Cartesian mesh, but here the cell next to the solid surface is cut into this polygon. Okay. So for example, here it is cut into a triangle here, so polygon here. So this is a type of cut cell mesh. So if you can't apply finite difference method over here, you have to apply the finite volume method. So this is the third approach which you can by which we can treat the presence of the solid surface. Okay, so Cartesian mesh is one of the main categories within structural mesh. The other main category is the body fitted structure grids, which are more common in the CFD community. And the keyword here is curvilinear. Okay, so there you don't stick to a Cartesian type mesh, which is purely orthogonal, but you adopt your mesh or you create a mesh in a way which is a curvilinear and which follows the curvature of the body itself. So there you don't have a perfect Cartesian mesh, but you have a structured mesh, okay, but it is fitted around the body. It is called body fitted structured mesh. And for simple geometries like this flow around an aerofoil, there are various categories, subcategories of body fitted structured mesh. For example, first one is the H mesh. So H means it resembles the shape of this alphabet. So if you see here, this is H shape mesh. Okay, this is like this. So two vertical lines, two vertical columns, and then one horizontal column. Okay, so this is a type of body fitted mesh, and this is what you have been generating in Fluent as well. Then you can also have a mesh like this. You don't have a H structure, but a C shape mesh. Then you can have an O type flow domain, O type domain as well. For very thin blades, like for turbine blades or compressor blades, we have a mesh like this, which is called sort of an I mesh. In these terminologies or mesh types exist for very simple geometries, and which is rare nowadays. But it started off like that. So for complicated structures and geometries, you create what we call multi-block meshes. And multi-block meshes can be have matching boundaries or non-matching boundaries. Matching boundary means that, for example, here, this is one shape, this is one block, this is another block, and this is another block. So three blocks, so they are multi-block. So each block has its own mesh. See it. Then at the boundary of these blocks or at the interfaces, there is a one-to-one matching of nodes across the boundary. This is called a matching boundary mesh. And here you can see there is a not one-to-one matching, but it's a non-matching mesh. Okay. There is a disparity here. See that the interface is not matched. Okay. So normally, people use this matching boundary mesh because, again, to cater for this non-matching boundary, the flow solver should be written in such a manner that it could transfer the information across this boundary in form of, for example, interpolation, which is an additional overhead. So this is another example of matching and non-matching. So that the underlying mesh is coarser, it's bigger in size, but to capture these small bolts or structures over here, have a smaller mesh. Okay, and then you have to match or unmatch depending upon the flow solver. You can have to create a. So for example, if this is a smaller mesh and this is a bigger mesh, then obviously you will have a non-matching interface. Then you can have a combo of CH mesh, HOH mesh. This is very basic. For internal flows, for example, this 2D pipe flow, 3D pipe flow, you can have a very good quality mesh like this, where your blocking will be something like this. First, you have to create this block, so one block, two blocks, and then third block like this, and then fourth block like this, and the fifth will be this side. And then you can mesh each region. Okay, for more complex geometries, another option is what we call overset meshes or chimera grids. So, for example, if this is a flying structure or something like that, aeroplane, and this is the one of the planes, can be a symmetry plane. So, on first we create a background mesh, and then for each of this part of this, for example, object, you create a separate mesh, and then you overlap or place each mesh on top of each other. So here it is a zoomed in view. You can see there is a background mesh, which is sort of more orthogonal, Cartesian type. And on top of this, we have a broadly fitted mesh or curvilinear mesh. So these two meshes are placed on top of each other. And then we use interpolation to transfer the information from this mesh to this mesh. So this was one of the approaches to cater for complex geometries while maintaining or keeping the structure grid. But this is not very common. As you can see that interpolation will be an additional computational overhead. And accuracy is also sometimes compromised. So to avoid the shortcomings of structure meshes to handle complex geometries, nowadays the major push is towards the unstructured grids. And of course, the main advantage is the ability to handle varying mesh shape and varying body shapes and sizes. So, as it is written over here, it can handle arbitrary shapes and geometries. And the other major advantage is that the local refinement can be done very efficiently in unstructured mesh. It's very easy to split unstructured mesh locally as compared to a structured mesh, because if you will split a structured mesh and if you want to avoid generation of a hanging node, then you have to split it all the way up to the boundary in order to have this avoid non-hanging nodes. Okay? So that will refine the mesh in those areas as well, where we don't need to capture the flow physics more accurately. But in case of unstructured mesh, you can split even a single cell as well, because they don't have to have this requirement of equal number of cells sharing a node. Here you can have arbitrary number of cells sharing a node. So that's why the local refinement becomes more easier than the structural mesh. So these are all examples of unstructured meshes. In unstructured meshes, we can have various categories, subclassifications, and the most common type of unstructured mesh is a triangular mesh or a tetrahedral mesh in 3D. Again, there are various algorithms to generate this triangulation of the domain, for example, Delaunay method, advancing from method, etc. Okay, we can have hybrid mesh as well, which is a combination of both structured and unstructured mesh. And why do we need hybrid mesh? So one of the main disadvantage of unstructured mesh is the loss of accuracy. It's generally less accurate than the purely structured mesh or Cartesian mesh. So in the regions, for example, where we have for higher and non-number flows, where we have this boundary layer present, or in the, so we need to capture these gradients more accurately. And there we need to have highly stretched cells with the large aspect ratios. And if we create unstructured mesh there, it will result in a loss of accuracy. So near the boundary, what we do is that we create a structured mesh, and away from this boundary, we create a unstructured mesh. So it's a combination of structured and unstructured. That's what is called a hybrid mesh. So here you can see, for example, uh, if you want to capture flow physics in this boundary layer region, you will require a high aspect ratio, means the x delta x is larger than delta y, or it is called also called stretched cells. Okay. So here you will have a structured mesh near the boundary, and as you move away from the boundary, you will have an unstructured. So there you can see a structured mesh and unstructured mesh away from the boundary. So it's the best of both worlds. In the areas of more important flow physics, you will have high accuracy, and away from uh, areas which are less important, you will have a coarser unstructured mesh. You can also create unstructured quad and hexagonal. So quad for 2D and hexagonal for 3D. Because it will have the advantage that generally quad shapes are more um, accurate or hexagonal in 3D, and they also require low memory storage as compared to triangular or tetrahedral meshes. So here is an example of unstructured quad mesh. It looks very similar to Cartesian mesh, but if you see uh, carefully, although we have quad meshes, but these are unstructured because, for example, this node over here is sharing 3 cells, but this node over here is sharing 4 cells. Okay, so it's an unstructured mesh in the sense that each node doesn't strictly shares equal number of cells. They have different number of cells being shared by each node. So this is, in a sense, an unstructured quad mesh. Okay. Then you can have arbitrarily shaped elements as well, but of course you need more experience to generate those kind of meshes. An example, arbitrary shaped elements, we have these polygons or these other type of polygons over here. So they are mainly used for mesh adaptation or for specific algorithms for for convergence accelerations like multi-layered algorithms. I won't discuss that here, but they do have specific applications, although they are not generally used for common meshing purposes. Okay, mesh adaptation is another important area of research. So here, what does mesh adaptation mean is that you only refine or de-refine your mesh depending upon the fluid activity, or for example, where we have large gradients of the flow quantities available. So for example, here we have this local refinement to capture the drag mode. For example, here this was the initial mesh. You ran a solution on it, and then there is a shock around it. On the upper surface of the aerofoil. And here you want to capture uh, the flow behavior also around this curvature of the leading edge and trailing edge. So you have these algorithms available in the meshing programs, which depending upon the flow activity can refine the mesh only in those regions where it is required. And away from those regions, we can have coarser mesh. So this clearly has an advantage because if you will keep on refining all the mesh in away from the zone of important flow physics being developed, then you will incur a large computational or very high computational cost because you will be unnecessarily solving in those regions where it's not important to resolve the flow. So mesh adaptation is a more efficient way of only uh, resolving those regions where we have large flow gradients or where you capture flow physics more accurately. Generally, that area is either around this solid surface or in the wake region or in the shocks region or the separation zones or recirculation regions. So this is another type of mesh adaptation where instead of refinement, you have moved the mesh to those regions, sort of stretch it to those regions where it mattered the most. So again, it's another example that you have created a local refinement. Mesh movement basically is another type of mesh movement. So the number of cells is same, but you have kind of stretched it into those regions where it mattered the most. So this is mesh refinement type mesh adaptation, and this is the mesh movement type mesh adaptation. Okay, grid quality. First thing to keep in mind is that you will be creating a non-constant size mesh. For example, here, as you can see, the cell size is increasing gradually. So what you want to avoid is that you should not create a mesh with a sudden jump in the cell size. So for example, here you can see there is a gradual decrease in the cell size, continuously decreasing size, or a continuously increasing size. So what you want to avoid is that you should not directly jump from this size to this size over here, or this size to this size over here. And in case of structured mesh even, so there you can also see the size is decreasing gradually. Okay. So you should avoid directly jumping from this size to next layer of about this size. Okay. So this will create a sort of convergence issue because the numerical scheme or solver will not be able to handle it more efficiently. Something which you should keep in mind. The other thing which you should do is that you should avoid creating skewed meshes or a diamond shaped mesh or something like this. So if you're creating a triangular mesh, then you should try to keep it like equilateral triangle, not like a highly skewed triangle. And similarly, if you're creating a quad mesh or hexagonal mesh, then you should avoid creating a skewed mesh. This also compromises the accuracy and convergence behavior of the solver. There are various matrices by which you can judge the quality of the mesh, and normally that are available inside the meshing program itself. You can create a sort of a report about your mesh quality, which will give you the aspect ratio and the skewness factor, etc., and the angle of skewness as well. So there should be aspect ratio should be as close to 1 as possible. So delta x should be equal to delta y, apart from boundary layer resolution, where you need more kind of structured structured stretched meshes where delta x is much more larger than delta y. So away from the boundary layer, you should try to create a mesh which is have a more aspect ratio closer to 1. Similarly, you should have a very low skewness factor closer to 0, and the angle between adjacent sides should be orthogonal or 90 degrees. So highly distorted cells like diamond-shaped cells or parallelogram diamond-shaped cells or highly skewed triangles will compromise the convergence rate and accuracy of the solution. Yeah. Especially in the high gradient region like in the shock wave region, you should have a good quality mesh and a refined mesh. And away from these more important areas in the far field, you can have these restrictions relaxed a bit. Okay, so that is all about mesh types and guidelines about creating a mesh. Any questions? Okay, so that completes the theoretical part. Now coming back towards the more fluent tutorials, here I want to just quickly go through 2 or 3 tutorials, and I won't be going through all the steps of these tutorials, but we'll be highlighting what we are learning in these tutorials. And later on, I will upload the complete tutorial which you can follow, and it will have all the steps there. So the first one we are going through today is the vertical axis wind turbine. And the main feature of this tutorial is that here we have a rotating region. So far, what we have been doing is that we only had stationary bodies. So, for example, in internal flows or external flows, like a 3D wing was stationary and the flow was, the air was flowing around. So, what to do? What options we have in Fluent to simulate moving bodies like this moving vertical axis wind turbine where the blades are rotating. So first let's talk about the problem over here. So we have this vertical axis wind turbine with 3 blades, and so these 3 blades are moving in with a 40 RPM, 40 revolutions per minute. There is a uniform velocity coming in with 10 meters per second. And this diameter of this hub is 12 centimeter, and the length of these blades is 2 centimeters. And the center of each blade is located. So this center is located 0.04 meter from this center of the hub. So what we are assuming is, we are making quite a lot of assumptions. First assumption we are making is that the turbine is already spinning independent of the flow. There is a flow coming in, but we are not simulating itself the effect of this flow and the result of this flow on the blade. We are assuming that under the influence of this flow, the turbine is already rotating with the constant RPM of 40 degrees. This is a very important assumption because in reality, what should happen is that Your flow should dictate, or the velocity of incoming air should dictate the RPM, or the forces being developed. But we are simplifying it, and we are assuming that the turbine is already spinning with 40 revolutions per minute. So this is one of the assumptions. Second assumption we are making is that instead of creating an assuming a proper aerofoil structure, we are assuming these plates to be the flat plates of dimensions 0.1 width and 2 centimeter length, and positioned on a pitch angle of 20 degrees. That means that the plates are placed such that when they are at the uppermost part, so when they are here, for example, uppermost part of the trajectory, they form an angle of 20 degrees with the horizontal. So this is the horizontal axis. So when they are here, they are at 20 degrees with the horizontal. So that's another assumption. Then we will have a domain. So we will have these three blades. We have this inner zone or the hub region, and then this will be our far field. We can have circular far field, or we can have a rectangular far field. So it's up to you. So at the far field, we have these conditions. So this will be our inlet. That will be our outlet. So at the inlet, we have velocity of 10 meters per second, and at the outlet, we can have a far field pressure of 101325 Pascal. Okay, so what options do we have in Fluent to simulate such a problem? So first major difference you should observe is that in here we have some parts which are moving, or some zones which are moving, and some parts which should be static. Like this, far field should be a stationary part because it's a far field containing our inlet and outlet conditions. But within this, so in the inner region, there are zones, for example, these three blade zones, and this hub will be rotated. Okay, so first thing will be that you will create a separate mesh for each zone, and then you need to kind of match those zones or stitch those zones together so that the information could flow from one zone to another. We'll see that later. But what options do we have to influence to simulate this kind of problem? So we have three options, which vary from very simple assumption or very simple steady flow simulation to complex 6 degrees of freedom solving. So a very simple way of doing it is simulating this type of problem in a steady manner. So what does that mean? So this is the inner region, is the hub, and these are the blades. So what you do is, so simplest option is to go for a moving frame of reference simulation. So what does that mean is that you set the fluent as you set the problem as a steady flow, although in reality it's an unsteady flow, and because we have a rotation over here, and there will be vortices shed from, and they in reality it's an unsteady problem. But to be more simplistic, you set it as a steady flow, and then you give then you set this inner zone and these three zones around the blades as a moving reference frame, moving frame of reference. So give it, so you keep the mesh static, but you tell the solver that this zone is moving with a velocity, okay, with a certain RPM. That's the simplest type of thing. Okay? So the blades will stay as they are, and the mesh will still be static. It will not be a moving mesh, but you will be telling the solver that this region is rotating with a certain RPM. So that's the simplest approach. That is called moving frame of reference method. Subzone condition is moving frame of reference. Then if you want to be more realistic, there is another second more advanced option, that is what we call moving mesh or sliding mesh option. So in that one, in addition to telling the fluent or the solver that this zone is rotating, you also uh, give a rotation to the mesh itself. Okay? So the second advanced stage is that you assume a certain constant RPM, which is 40, and you also tell the solver that this mesh is also moving. So each zone mesh will also move with the certain RPM, that will be 40 RPM. And that is used for unsteady flow simulations where you want to move the mesh around and move the blades around. So in the first one, in the steady one, we just simulated the effect of this rotation. And the blade itself and the mesh itself was static. We just gave it a certain velocity, RPM. And in the second one, for unsteady case, we also are moving the mesh. And that is more realistic that because it will also cater for effective flow field or effective vortices shed by each blade on the upcoming blade. Okay, so if this blade is moving, this will shed vortice, and this will affect the upcoming blade here. So if you want to simulate the effect of vortices or wakes, you should go for unsteady flow simulation. And the most advanced option is, there's an option there which we call the 6 degrees of freedom solver. And there you can truly simulate the effect of oncoming or incident wind on this instrument. So there you gave a 40 RPM velocity in the first two cases, but here you will only prescribe that, okay, this much wind velocity is coming. Now it will calculate the RPM and the resulting moments of forces and the velocities itself. So this is the most realistic option where you let the fluent or you let the solver decide itself or calculate itself the RPM. So here in this tutorial, we are only restricting ourselves to first two cases. Okay, this is more advanced option. If you're interested, you can go for to look online for more resources there. Okay, so what are the steps involved? So steps will be that, as I said before, that each of these zones, so this is one zone, this is another zone, this is another zone, and this is another zone. So there are 4 zones over here. Then we have this outer zone, which is the far field zone. So we have 5 zones over here. And between these two zones, for example, between this zone and this zone, to transfer the flow of information, we need to match the interfaces. So that will be the first step, that we need to tell the solver that these, where are the interfaces are between these two. Now this is a very important step, because sometimes people, what they do is that they define separate meshes and they define certain RPMs, but they don't tell the solver to match or let the solver let the flow information from one zone to another in the form of defining interface zones. So you need to create interface zones if you're creating, if you have local moving meshes or local revolving parts. So that will be the first steps, set interface zones. And the second one will be set zone conditions. So, so first you need to define interfaces. You need to tell that they are 2 separate zones and they are exchanging information. Then once you have done that, you move towards this step over here, zone conditions. Then you need to tell the solver that if this is the zone, it's centroid, and if it is moving, it's moving relative to what, and it's moving with how much velocity. So that is a part of what we call zone conditions. And then there will be remaining boundary conditions. For example, in the far field, we need to set up the inlet boundary conditions and then the outlet boundary condition and the wall boundary conditions for the blades itself. Okay, so there will be four mesh interfaces. I will show that to you later that actually this circle over here has basically two parts which are overlying each other. Basically, these are two parts, two circles which are overlying. One circle belongs to the outer zone or hub zone, and one circle belongs to the this blade zone. So they need to be overlapped or matched in order to create a mesh interface. And this one circle is called relating to the this zone, smaller zone is called bottom blade inner circle, and then we will have a outer circle which belongs to this hub zone. I'll show that to you later. And then, so in the similar sense, we will create interfaces for these three blades and the hub zone, which will be the interface with the far field zone itself. Okay, so then the next step will be, because each zone is rotating, this blade zone is rotating, so we need to give it a certain, so we need to specify the origin of rotation, rotational axis origin. And so this is the global origin which is placed here. So your global origin x0, y0 will start somewhere here in the center of the hub. So you need to define the centroid of this region, this local region. And this centroid or this origin you can calculate by using this formula. For example, for this top blade, this is located at 120 degrees from this global coordinate axis. So, and this is 0.04 meter away. So its x coordinate will be 0.04 meter into cos of 120 degrees. So that will be x, and similarly there you will determine y. In a similar manner, the centroid of this and these zones are given over here. Okay, angular velocities are mentioned as 0, 0, and 0 for these three zones, because what we are doing is that will be defining an absolute velocity of 40 rpm for the inner zone, or what we call the hub zone. Okay? And relative to that 40 rpm, will be defining the velocities of these three blade zones, which will be, so relative to that it will be 0, but absolute frame of reference, this will also be moving with 40 rpm. Okay? So we'll see that later. So let's quickly show you I was talking about. So in this case, the geometry and mesh are already given to you. And I uploaded the mesh file, WAWT mesh.msh last week. So you can see it in the uploads there. It will be there with the name WAWT.msh. So we are skipping geometry and meshing stage. We are just importing the mesh file and loading the code. So this is the overall domain. So this is the far field. And if you will zoom in here, you will see that inner. So as you see here, this is the hub region, and these three regions are the blade zones. So you can monitor it, display it one by one. Okay, so here comes the interfaces. For example, for bottom blade, which is on the left bottom, I have just highlighted two edges over here. And if you zoom in, you will see that they are sort of overlapping each other. So these two are the edges or boundaries which need to be stitched together in the form of interface. And we need to tell the solver that this is an interface, which is being shared by the outer hub region and the blade region. So in total, there are 6 circles, so 2 for each zone. Similarly, for far field, for the hub inner and hub outer, we will have these 2. Similarly, you have these blade shapes as well in the form of flat plates. So you can, so once you load it, you can display them one by one in order to have a more clear idea of what I'm talking about. Okay, so this is the overall domain we have. So one thing which we are need to do is that for angular velocity, the default are radian per second. We need to convert that into RPM. So we need to tell the solver that take the angular velocity in units of RPM. Okay, so first step, as I discussed, that you need to create the interfaces. So how do you do that? First, you select that, go to the boundary condition, and first you need to set the boundary condition type as interface. So there are 2 such circular edges for each blade zone. So 3 blades, 6, there will be 6 interfaces. So you need to change the boundary type to interface for these 6 shapes or circles one by one. So once you change it, you will see that there will be a new group being formed with the name interface. So with this 6, and for the hub, this inner hub region, there will be another interface. So there will be 4 interfaces will be created. So then below you will be see a mesh interface tab. So double click on that, and then you need to name the interface now. So you need to tell it which two circles are overlapping. So for example, for bottom blade, we selected this bottom blade inner circle and outer circle. Similarly, so you pick up each pair one by one and stitch them together to create an interface. So in this case, top blade will be selecting top blade inner and top blade outer. This is the hub region. the inner bigger circle. So this is how you create the interface to allow the flow information from one mesh zone to another. So once you have done that, then you set the usual parameters like what is the flow solver, what turbulence model we're using here. We're using K epsilon, realizable. So materials will leave the air. And then in the cell zone conditions, so there comes the second important step. So previously what we had was that we only had one cell zone in all the previous cases because there was only one mesh, one consistent continuous mesh. Now here, because we have a number of separate zones, for example, we have 3 blade zones, then we have hub zone, and then we have this overall zone, which is the far field. So because we have a number of cell zones, we need to specify the properties of each zone. For example, there are some zones which are static. In this case, this will be the far field. And there are some zones which are rotating. So how to prescribe the rotatory motion? That what we do is that we do in the cell zone conditions. And remaining, whatever the boundaries are, how they are treated in the boundary condition tag. So the rotation or the static properties are prescribed for each zone in the cell zone condition tab. So here, have a look on how we prescribe the motion. So first we have selected the inner zone, which is the hub zone, and we are giving it a rotational velocity of 40 rpm. That's it. And if you look here, I go back. So how did we start it off with that? So inner zone, you click on frame motion, that is you prescribing that it's moving. And relative to cell zone, you are giving an absolute velocity of 40 rpm. That's it. And the rotation axis, if you look here, yeah, so it's rotating with respect to the global region, which is placed at its center, which is coordinates 0, 0. Okay, so then you move towards each of the 3 blade zones. So for example, starting with top blade zone. So just show you what I'm doing. So what we have just done is that for this hub zone, we have prescribed a motion of 40 rpm in the absolute sense. Okay, we have created these zones, and we have just prescribed zone condition for hub zone. Now what we are doing is next that we are taking this inner zone now, which is the blade zone, and we are prescribing the motion of this zone relative to this inner zone. So because this zone and this zone both are moving with 40 rpm, so in absolute terms, this absolute frame of reference, this is moving with 40 rpm, and relative to this inner zone, these blade zones are moving with a relative velocity of 0 rpm. But in absolute sense, they will be, of course, moving with the same velocity as the hub zone is moving. Okay, so here you need to prescribe the relative motion first, and what is the rotational axis origin for each of these zones, okay, which is prescribed over here. So that's what we are going to here. So first thing which we have done is that we are relative to cell zone. Now instead of absolute, what we have mentioned over here is inner. That calculate the motion, or it is moving with respect to inner. I go back again. So we are prescribing that this blade zone is moving relatively relative to which zone? Inner, with a RPM of 0. We have left it at 0 because it's a relative velocity. So if we had chosen absolute, then we had given a 40 over here. Okay. And then we need to also prescribe the stated axis origin, which is the centroid of this inner zone. Centroid of this inner zone relative to the global region. So these coordinates which are given over here, we need to mention those in this rotation axis origin. That's it. So that step we'll be repeating. I'm skipping that for each of the blade zones. Okay, so that's done for cell zone conditions. Next, we will be describing the remaining boundary conditions. For example, in the far field, we need to prescribe the inlet velocity of 10 meters per second and a certain turbulence. So that you can see yourself later. Similarly, you'll be prescribing far field 2. And for the blade walls, we have blade walls. So zone conditions we have prescribed, but bounding conditions we need to prescribe. So in that case, the blade or blade walls, you need to select the boundary type as wall, as expected. But instead of stationary wall, you need to mention moving wall over here, because the blades are also, walls are also moving with the rotational velocity. And you need to give the rotational axis origin, which are the same coordinates we set for each blade zone in the cell zone conditions. And here we have described the motion relative to adjacent cell zone. So it will just pick that velocity with which the cell zone was moving, which is 40 rpm. If we had chosen absolute, we would have prescribed the velocity as 40 rpm. So in the same manner, you also set the wall boundary conditions. You can also copy. So once you have set a condition for bottom blade, you can just copy it to the other. But keep in mind that you have to change the coordinates of the origin. So that you can see later. And then you set the other parameters. For example, in the remote definitions, report definitions, you are interested in, for example, the coefficient or the moment being produced by the rotation. So you can set a report definition to calculate the moment coefficient for each blade. You can analyze that later. Okay, so then you initialize it using hybrid initialization. You are interested in what is the magnitude, so you need to tell the solver that also calculate the additional quantities like what is the magnitude. You can observe it, and then you form the simulation, and then you post-process it, and you monitor various contours of velocity, pressure, etc. Okay, so I'm not going through that. You can just follow that once I will upload the complete tutorial. Okay, so that was the study part of it. Now, how to prescribe? Uh, so so moving one step further, how to simulate unsteady flow using moving mesh method or sliding mesh. So that is a kind of more advanced or more realistic simulation of this one. So there's only one point there, which I mean, by which you can just convert this problem or tell the solver that now solve a moving mesh problem. So it's the same problem, and I'm uploading. Okay, this tutorial for the unsteady starts with some of the post-processing which was left of the study part. For example, the observance of the what is the magnitude. So it is, you can observe those or follow that. So okay, moving towards unsteady. So once you load, you can load it from the already solved study problem. Just need to double check that everything is right, all the conditions which we prescribed. So it is double checking only. Okay, so in order to tell the solver that now the mesh is also moving and we are going to solve unsteady problem, just need to make one change or one enhancement. Click on cell zone conditions, and first you go to the inner cell zone conditions. So all the things remain the same, plane motion, absolute, whatever. And here there is a tab which says copy to mesh motion. Just need to click that, and that's it. Now we are telling the solver that our mesh is also in motion or moving, and whatever the properties or for moving frame of reference, just copy those properties or those values to the mesh itself. The mesh, we are telling it, okay, move the mesh also with the speed of 40 rpm. So that's it. You just need to click copy to frame motion. And so you need to repeat this for each smaller blade zones as well. Copy to mesh motion. And everything you'll see that it will just copy the same properties in the mesh motion. That's it. So that is for that, but when starting the simulation, you also need to tell it for unsteady flow simulation. So there you need to select the transient option as well. If you'll follow this, probably it's done somewhere. So I just need to mention that. Okay, and then we do that. This is done. Okay, here somewhere there is an option where I mentioned that you can also create the animation of the unsteady flow in Fluent itself. So somewhere here, I've just clicked some tabs over which you can follow. Otherwise, a good option is always to go for CFD post and not do all the post processing there. So these are all the steps mentioned how to save data for later post processing. Okay, so then you run the unsteady simulation. You set up the time step, number of time steps, and time step size, etc. And then you simulate this one. And here you can set up the animation properties and save that to a video. So once that is saved, you can run the video itself. So it's a vorticity magnitude. You will see an animation like this. So here you can see the blades are moving and the wake of each preceding blade is affecting the each following blade. So I'll upload that tutorial and you can visualize it yourself. So that was the main thing, how to simulate moving bodies. So again, I will repeat, you have three options. You can just set a moving frame of reference value and for steady flow simulation. And you can also set a sliding or moving mesh condition for unsteady flow simulation and to account for more realistic simulations, you can go for 6 degrees of freedom solver. Okay, next tutorial is about a flow in a 3D artery. So it's a biomedical application. So here what we are doing is, so we have so we have blood coming in. So this is the inlet and then it's a bifurcating. So this has two branches. This outlet 1 and outlet 2, and then certain wall conditions and outlet conditions are prescribed. Okay, and then outlet pressure, etc. And here, what I want to demonstrate is that how we can create a local mesh refinement, which we just discussed. Here we'll be creating an unstructured mesh, but how we can create a local refinement within that unstructured mesh using a method called sphere of influence. If you remember last time in the 3D wing unstructured meshes, we created a body of influence. So body of influence can be any shape. Okay? In that we created a box, 3D box. And here we can also create another body of influence for local control of mesh sizing, which we call sphere of influence. So it will be a more like a spheric body. And here also the other thing in the meshing is how to introduce inflation layers. Inflation layers again refer to that how we can create a hybrid mesh. So hybrid mesh, I just mentioned that to account for boundary layer effect on near the solid surface, you create this structured mesh, and away from solid surface, you or the walls you go for unstructured mesh. So that will be, so hybrid mesh will be generated, and you see that how we can create an hybrid mesh using inflation layer. So again, this tutorial has two parts: a steady one and an unsteady one. In unsteady one, they are using a user-defined function, inlet velocity specification. So it's not a constant inlet velocity, but a function-related velocity. And there you will observe that how we can load a user-defined separate function as inlet condition. And also, you will observe that if we want to track the motion of blood, for example, and if we want, for example, introduce some particles, we want to track the motion of those particles as they move inside the body. So how to introduce the particles or injections and how to track the motion of those particles. Remember, this is the unsteady simulation. So if we had steady simulation, we can just follow the streamlines. But for unsteady simulation like this, we can introduce some injections or particles and then can track those particles. So let's start with this tree. Again, the geometry is provided to us, which I have uploaded last week, I guess. You can see it there. So geometry you will import, and then you can import it to look like something like this. So I'm come directly to the mesh. So I start the mesher, and then I import the same geometry. It will upload the same imported geometry. You need to change the units. Okay, so to create a variable mesh sizing, first you need to prescribe the body sizing, the overall mesh size. So you select the body, and for example, you can give it a element size of 1 millimeter. Now, in order to create a localized refinement, you first need to create a local coordinate system. So here we are creating a local coordinate system around which we will be creating a body of sphere. A sphere of influence. Okay, so then you select sizing again. You select that body, and now here in the type, you ask it that this sizing will be a sphere of influence, which is located at a new coordinate system you just generated. And here you will see that you are giving what will be the diameter of the sphere, how much larger you want to create in local refinement region. So as you will see later, it will refine the mesh only in that sphere. And there we are prescribing a element size of 0.5 millimeter. So in this body sizing, away from this sphere, we prescribed a sizing of 1 millimeter, but here in this region, we are going for half of that size, which is 0.5 millimeter. So this is how you can create a locally refined mesh zone. So next thing it is doing is it's creating a hybrid mesh. So we are prescribing an inflation layer. So inflation layer, for inflation layer, we need to tell it all the walls. So what will be the boundaries? So you need to select all the, so you need to go select all faces, including inlet faces and outlet faces. So once you've selected all the faces, you also need to select inlet, these two. So these are two outlets. This is the inlet. So you need to, in the boundary tab, you select all the faces, including inlet and outlet. So there will be 122 faces. Okay, now inflation options, there are many inflation options. You can prescribe what will be the first layer thickness. Remember Y plus. So if you know the Y plus, you can just, depending on the Y plus, you can prescribe the first layer thickness. Okay, what will be the layer of first cell adjacent to the wall. You can also prescribe first aspect ratio, last aspect ratio. And you can also prescribe, but with the total thickness of this inflation layer, including all the cells in the, so it will be the total thickness of uh, the layer of, for example, if you're generating 5 cells in the y direction. So what will be the total thickness of those 5 cells? So here we are prescribing total thickness. Okay, then we are prescribing that, okay, create 5 layers of such structured cells with a growth rate of 1.2. 1.2 means that if the first cell adjacent to the wall is of 1 millimeter, then the next layer of cells will be have a width of 1.2 millimeter. So that is 1.2 times than that. And then the third layer will be 1.2 times the size of second layer and so on. So that is the growth rate. And the maximum thickness is 0.6. And once you have prescribed all of these, you can just say generate the mesh. The inflation algorithm means that how do you want to create the inflation? First, generate the uniform mesh and then go for inflation or hybrid mesh, or just start the hybrid meshing process from the start. So depending upon your problem, you can go for pre or post. It doesn't matter as much. Okay, so the meshing is done. And if I just rotate it, you will see that because we prescribed a sphere of influence here, where the mesh size of prescribed as half from that of outer region. So here mesh size is 1 millimeter. So each side is 1 millimeter. And here in this region, we have half of that. So here you can see an example of a local refinement. And here we have defined the mesh because this region is important. Here we have shear stress developing, and here there are some large gradients also. So we particularly wanted to define this region in order to capture the flow physics in more detail. Okay, and then you can set the boundary conditions. When we go to the solver, it's a laminar flow, and you prescribe the, for example, you can prescribe the blood, as blood, set those properties. You will just follow this tutorial. You can follow this later. Then you run the simulation and you can visualize velocities, pressures, shear stress, the velocity vectors at various cross sections, etc. Shear stress regions, wall shear, something like that. Okay, so that's about the steady simulation. And quickly, I just want to mention what is the difference steady. So same mesh, same conditions, but there are a few modifications. So here the material properties are more advanced, but properties, they are more realistic. You can follow it. Then there is a UDF based inlet velocity prescription. You can follow that as well. I just want to mention infections. This is the usual boundary condition setup. Okay, now how you introduce, give it, tell the solver that we will follow a certain trajectories or flow particle movements. Let it finish with the boundary conditions. So we go to the physics, and in discrete phase, you go to the injections. Then you type, click create, and we are describing here massless because we are not introducing any physical particles, which is in addition to any other particles apart from blood. Of course, when you are using multi-phase calculations, then you can go for other type of injections as well, like inner droplet. So this is more about the multi-phase and multi-material flow simulations. So here we are clicking massless, and then you need to give it the position, the initial position or the coordinates where you will be introducing this particle. So at the inlet, we are introducing two particles at this arbitrary arbitrary coordinates or arbitrary locations. So you need to select section properties and then you need to give the location coordinates. Okay, so that was something which I wanted to point out. And the rest of the things are as per routine. So then you can also set up the unsteady flow simulation, storing the data for later post-processing. Okay, so once this unsteady flow simulation starts, so then when you go for the results, so this particle injection data you need to first store, and then you need to upload it in order to visualize those particles. So you can follow it later. Just want to mention that that's in the next file. So here are those injections. Okay, this is the trajectory of those two particles which we introduced at the inlet. You can watch it in more detail later, but just wanted to show you the animation. This is it. You can set up the animation in Plate. Then there you can see that you can track the motion of these red particles. So this is something I wanted to show you, that you have the capability in Fluent to perform such kind of simulations. And then you can see the rest of the unsteady flow phenomena as well. Okay. So that's about it. They were more advanced. Okay, we never did an uh, fluid flow problem with heat transfer. So here's a very simple scenario. We have a turbulent forced convection. So we have this pipe in which the flow is coming, but here in this uh, location, we have this heated section. So this upper wall has three sections. First section is insulated, then the middle section is heated, where we have a heat flux. And then this third part is also insulated. So here you can also simulate such kind of problems. You just need to prescribe the proper wall boundary condition, uh, which will cater for this heat flux. So we have heat flux of 5,200 watt per meter square. Just quickly show you how to prescribe that. So you do the usual stuff. Just need to split the upper. So we're taking the upper half using the symmetric assumption. So you need to split the upper wall into three regions. Okay, first two. So the front and rear will be insulated, and the middle will be uh, heated. So you need to split the domain as well, so that you could prescribe the boundary conditions later. Again, is coming towards the description of that. So once you load solver, and then you come towards the boundary conditions. The center line is neutral. Okay, so here's that region heated section. So this is wall again. But once you open that wall, you go to the thermal tab. Then in thermal tab, you can prescribe what kind of information do you have: heat flux, temperature, convection, radiation. So we have heat flux, so we just mentioned that. So that's it. That's what we do for prescribing heat flux. And then you run the simulation, and then you can observe the effect of that heated region. So here we have various contours where you can temperature contours, velocity contours, so forth. You can also visualize the wall temperature, upper wall temperature plot as well. So you see that insulated section, and then in the heated section we have a gradual increase in the temperature, and then in the rear insulated section we have a gradual decrease. So these were the tutorials, remaining tutorials which I wanted to highlight. I'll upload the complete tutorials. Thank you.